Hello, I'm Ryuichiro Hataya. I present our work, Meta Approach to Data Augmentation Optimization, which is a method to optimize a CNN and its data augmentation policy simultaneously. Before starting this presentation, I thank my co-authors Yan, Kazuki, and Hideki. Let me briefly introduce our work. We proposed Meta, which simultaneously optimizes a CNN and its data augmentation policy. We used implicit differentiation that allows fast and space-efficient implementation. Data augmentation for image recognition is something like this. Given a training image, we apply an operation stochastically with a certain strength sequentially. As a result, we obtain diverse images and virtually increase the number of training data. Here, we find some parameters. Probability, that is how often we apply the operation, and magnitude, that is the degree of strength to apply the operation, and combination, that is which operations we apply to images. So we want to design a data augmentation policy that minimizes validation criterion by tuning these parameters. Optimization of data augmentation policy can be written as a nested optimization problem. In the inner problem, a CNN is trained to minimize the training loss with a given policy phi. In the outer problem, a policy is optimized to minimize validation loss. Actually, directly tackling this problem is computationally difficult. So, existing approaches, for example, replace the inner problem with lightweight proxy tasks or redesign the search space of policies. However, questions arise, especially when we obtain a new dataset. Do we need to create a new proxy task or new dataset? And do we need to redesign search space for a new dataset? Different from these existing approaches, we try to tackle this nested problem more directly and propose meta approach to data augmentation optimization, in short, Meta. Here, like the inner problem to optimize the CNN, the outer problem is also optimized by an efficient gradient-based optimization method, namely SGD. To do so, we used a differentiable data augmentation policy. The difficulty here is that during validation, we do not use data augmentation, so we cannot use the standard backpropagation to obtain the gradient for policies. We circumvent this problem by using implicit differentiation, and we adopt Neumann series approximation to estimate Hessian inverse. As a result, Meta only requires double training time and memory compared to the standard training protocol. These are the empirical results. As baseline, we compare Meta with the standard training protocol without extensive data augmentation, fast augment, which uses a lightweight proxy task, and run augment, which restricts search space and uses grid search. As can be seen, Meta shows superior performance to these baseline models, which shows the importance of using the target task as in the problem and full search space rather than the restricted search space. In summary, we propose Meta, a method to simultaneously optimize the CNN and its data augmentation policy. Thanks to implicit differentiation and Neumann series approximation, Meta is fast and space efficient. We are looking forward to discussing this work with you. Thank you for listening.